Types of data, an introduction. The objectives in this demonstration are to introduce the different types of data and to differentiate between categorical and numerical data. We begin with types of data. In this section, we introduce many different ways to categorize data. And these categories include categorical data, numerical data, discrete versus continuous numerical data, and of course the nominal, ordinal, interval, and ratio levels of measurement. Some terminology. Data, this singular is datum, is information from a source. If the data is numerical in nature, then the data would be numbers with a context. Categorical data is data that refers to labels or names that do not represent measurements or counts. Numerical data is data that refers to measurements or counts. Here's an example of categorical data. For numeric style categorical data, we could have Social Security numbers, telephone numbers, zip codes, or bank numbers. Notice that each one of these have numbers associated with them, but they all perform some kind of labeling function. They do not represent a measurement or a count of any kind. Some non-numeric styles of categorical data include ethnicity, gender, religious affiliation, or a make of a car. Numerical data is further divided into two types, discrete and continuous. Discrete data is data that results when the number of possible values is either finite or countable. Continuous data is data that results when the number of possible values is infinite, that correspond to a continuous scale that covers a range of values without gaps, interruptions, or jumps. Here is an example of numerical data. For discrete styles of numerical data, we can have the outcome of a coin toss, the outcome of a die being rolled, the number of times you place a phone call in a time period, and the number of times you visit a relative. These are all either finite or countable values of measurement. For continuous kinds of numerical data, we have weight, height, time of birth, and stock prices through a time period. So these are measured on a continuous scale rather than a discrete scale. Here's a comparison between categorical and numerical styles of data. Categorical you can think of as either names or labels, and averaging does not make sense when you consider categorical data. For numerical data, these are measurements or counts, and averaging can be done, and it does make sense to average numerical styles of data. Another classification of data would consider the levels of measurement, and there are 4 subcategories to this classification. The first one is nominal, the second one is ordinal, the third one is interval, and the fourth one is ratio, and we'll describe each one of these in the following slides. Nominal level of measurement is characterized by data that consists of names, labels, or categories only. The data cannot be arranged in an ordering scheme, and differences have no meaning. Here's an example of nominal data. Political party affiliation, zip codes, answering a survey with yes, no, or undecided. These are all examples of nominal styles of data. Ordinal data, or the ordinal level of measurement, is characterized by data that can be arranged in some ordering, but differences obtained by subtraction between data values either cannot be determined or are meaningless. Here are some examples of ordinal data. Grades. It is understood that an A is better than a B in a course, but A minus B has no meaning. Ranks. It is also understood that being first in rankings is better than being second, but the difference between rankings cannot be determined. What does a rank 1 minus a rank 2 mean, in other words? This differencing cannot be done in a meaningful way. The interval level of measurement is characterized by data that has an ordering and subtraction has a meaning. However, data at this level does not have a natural zero. Here's an example. There are different measurements for the freezing point of water. On the Celsius scale, it is 0 degrees Celsius, but on the Fahrenheit scale, it is 32 degrees Fahrenheit. And on the Kelvin scale, it is about 273 Kelvin. There is no natural zero in this case. Another example is years. The Christian calendar begins with the birth of Jesus Christ, but the Islamic calendar begins with the Prophet Muhammad's trip from Mecca to Medina in about 1622 AD. Because of these differences in measuring the years, there is no natural zero. Now, these are just two popular examples demonstrating that the data for years has no natural zero. There are many other calendars in existence based on culture. The ratio level of measurement is characterized by data that can be arranged in some order. Differences can be performed and have meaning. And lastly, there is a natural zero, implying that zero itself has meaning in the data set. Some examples of ratio data include prices of commodities and distances traveled. Here is a chart that kind of summarizes the levels of measurement, a description, and an example for each one of these levels of measurement. So if you wish, you may want to pause the video here to take some notes. Where data comes from. In this section, we introduce the two main locations where data comes from, the population or the sample. We also include some terminology associated with these locations. So here's some terminology. A population is a complete collection of all individuals to be studied. A sample is a sub-collection of members selected from a population. A census is the collection of data from every member of the population. And here's some more terminology. A parameter is a numerical measurement describing some characteristic about a population. A statistic is a numerical measurement describing some characteristic about a sample. Some additional notes on parameters and statistics. We always collect data from a sample, so measurements we collect would be statistics. We oftentimes estimate or test claims about measurements describing an entire population, so we never know parameters. And here's some more terminology. Practical significance is the use of intuition or quote-unquote common sense to determine if an effect is feasible. An observed effect so large that it would rarely occur by chance is known as statistically significant. So here's an example that kind of separates out the population, the sample, and the census. Suppose we wish to determine if the opinion that Chinese people are shorter than other ethnicities has some validity. Suppose we measure the heights of all people of Chinese descent in the state of North Carolina, along with the heights of all other people in North Carolina as well. What would be the population, the sample, and the census for such a data collection. The population is all people of Chinese descent in the world. The census would be the height of every person of Chinese descent in the world. And the sample would be the people of Chinese descent in the state of North Carolina. Here's another example. Suppose we collect data from a sample that shows an average score of 15.20 units. We know the population has an average score of 17.76 units. Which measurement is the statistic and which is the parameter? 17.76 is the parameter, as it is a measure of the population, while 15.20 is the statistic, as it is a measure from the sample. Here is an example of statistical versus practical significance. In a test of the Atkins weight loss program, suppose 50 subjects using that program had a mean weight loss of 3.2 pounds after 1 year. After formal statistical analysis, we deduce this to be statistically significant. That is, based on statistical criteria, this diet is shown to be effective. Is this actually the case? Probably not of practical significance. Individuals engaging in a weight loss program would most likely be looking to lose more than 3.2 pounds. And so this is the difference between statistical and practical significance. Your mathematics and your measurements and all of the statistical analysis that you perform may lead you to a statistically significant result. But if the overall performance is not up to par by measuring based on intuition or a quote-unquote common sense criteria, then it's not of practical significance. Here's another example. Let's consider the following situation. Suppose in a test of the Atkins weight loss program, 50 subjects using that program had a mean weight loss of 33.2 pounds after 1 year. After formal statistical analysis, we deduce this to not be statistically significant. That is, based on statistical criteria, this diet is shown to be ineffective. Is this actually the case? While the statistical criteria for significance was not met, losing 33.2 pounds on a diet may be enticing for individuals attempting to lose weight. And again, this is the statistical versus practical significance. In this case, we kind of reverse the roles. This was practically significant, but our mathematics and statistical analysis showed that it was not of statistical significance. In this section, we introduce symbols that are commonly used in statistics courses. For the population symbols, we often have this little symbol here, the Greek letter mu, and this is often used for population mean. We have the Greek letter sigma, which kind of looks like a referee's whistle, and this is used for population standard deviation. This funny looking P is the Greek letter rho, and this is used for population correlation coefficient. And the Greek letter pi is often used for population proportions. For sample symbols, we have x bar, which normally represents the sample mean. We have a lowercase s, which generally represents the sample standard deviation. We have a lowercase r, which usually represents the sample correlation coefficient. And we have a lowercase p, which often represents the sample proportion. Now, these are commonly used symbols, and these are their commonly used definitions for these symbols. But please note that you have to read over your text or read over the text that you're using to make sure that these symbols still have those meanings. Here is a list of more symbols that are commonly used. The Greek letter alpha is used to denote the probability of a type 1 error, rejecting a hypothesis that is accurate. Alpha is also used to measure the significance level, and it is by no mistake that the same letter is used to measure both, because they both measure the same thing. The Greek letter beta is used to denote the probability of a type 2 error, and that's often classified as failing to reject a hypothesis that is inaccurate. The Greek letter chi is used to denote a type of distribution. There are chi distributions, and there is a chi-squared distribution that's commonly studied in statistics courses. The capital sigma is used to denote the sum of values. Thank you for your time and attention.